Okay, I wanted to show you a special case that might occur. Maybe it's not all that special. It totally has the possibility of occurring anytime you're solving a system. And that possibility is that you end up with infinite solutions. So let's take a look at what that looks like in solving this system. I did also something with equation 2. I threw a fraction in there. It looks like a standard y equals mx plus b form equation. So I did that so that just to illustrate something that you come across in common. And in fact, I'm going to work with equation 2 first to get it into that standard form, ax plus by equals c, and then I can line that up with the first equation. So the first step that I'm going to do with equation number 2, leave a little space, is to I'm going to eliminate that fraction, the 1/3, and it's really easy to do. I'm going to multiply everything by 3, the denominator that I see there, because 3 times 1/3 is 1, and it makes that fraction go away. If you have several fractions, you can multiply the entire equation by the common denominator, and that will clear the fractions. It's a nice technique. So it's not totally necessary, but it is nice. Let me multiply everything by 3. That gives me then, for equation number 2 thus far, 3y is equal to x minus 6. Again, 3 times 1/3 is 1, and 1 times x is just the x right there. Okay, one more step to get it into the standard form. Subtract x from both sides. And that gives me negative x plus 3y equals negative 6. Why did I put the plus there? Because that 3y is positive 3y, so I'm allowed to do that. Now I've got both equations in standard form. Equation number 1 is negative x plus 3y equals negative 6. Equation number 2 that I just manipulated there turns out to be negative x plus 3y equals negative 6. Interesting. They turn out to be the same equation. What that means before I continue with the process of elimination is, graphically, same equation means the same line. So these are really one line right on top of each other. They're the same line, which means that they share every point. A point is a solution on a line. A point where lines cross is a solution to the system of equations. Since they touch at every point, there are an infinite number of solutions to this system. But let me proceed with the addition step just to see what this looks like as you're moving along. Okay, and actually, I lied. I'm not ready for the addition step yet. What I need to do is erase this, for one. Okay, there we go. Sorry about that. I don't fib on purpose. Sometimes it happens. Oops. I didn't mean it, I promise. Okay. What I need to do is prep the system for elimination. In this case, multiplying either one of those equations by negative 1 is going to do it. So let me just put a parenthesis here, multiply everything by negative 1. This times negative 1, this times negative 1, and this times negative 1. What that gives me then is the following. Equation number 1 is still negative x plus 3y equals negative 6. Equation number 2 is positive x minus 3y equals positive 6. And here's what we get when we now add the system together, the weird thing I was talking about. Negative x plus x is 0. Positive 3 plus negative 3 is 0. So on the left side, I get 0. Negative 6 plus 6 is also 0. Where did all my variables go? This is why I'm pointing this out. If you get something like 0 equals 0 or 5 equals 5, this is certainly a true statement. It's always true. Okay, it's never false. And this comes with an implication. The implication is that you have infinite solutions. Okay. However, again, if you think about these as lines on a graph, it doesn't mean that any point on the graph is a solution to this system. It has to be points that are on this line or this line, which are in fact the same line. So the way we specify that is the following. Here's the answer, okay? Here is the answer, the solution to the system. We can use set notation to say that we're looking at the set of points x, y, such that one of these equations is true. Negative x plus 3y equals negative 6. And then we end our set notation. What this says is that every point that can be listed as an ordered pair, every point, is a solution such that it obeys this equation. Okay, so any number for x and y simultaneously that shows that this equation is true is a solution to this system. Any x and y point that does not satisfy this equation is not a solution. So be careful, especially when you have infinite solutions. What you're looking at really is a constrained set of solutions. Even though you have an infinite number of them, they are constrained by that equation.